All right, 1.1e exponential functions and percent change. This is part A of 1.1e. So we're going to start here with Sandy collected 10 pounds of apples at an apple orchard. She is determined to eat 20% of the apples remaining every day after the day she went to the orchard. Write an exponential function to model the scenario and use it to estimate how many pounds of apples she has left after week 1. So the first thing you want to make sure you all understand is what an exponential model looks like. So an exponential model means you're in the form of y equals a times b to the x. That's what it means when it says exponential model. Okay? Questions so far? Okay? When you're an exponential model, your a represents your initial value. So your a is your initial value. Okay? Your b is what we call our growth factor. So your b is your growth factor. To tie this into what we talked about tables, that's our ratio, right? How did I get from one number to the other? Okay, that's our ratio. Okay, what we're also going to talk about is your percent change. Your percent change is what you are increasing or decreasing by. I mean, it's good to write. You should have room at the top. Increasing or decreasing by. Okay. All right. So these are things that you're going to hear me saying while we're doing this. So it says here, she's determined to eat 20%. So eating 20%, that's our percent change. Does that make sense? So this is our percent change. I'm just going to write PC. Are y'all fine with that? Okay. And she's eating, so is that an increase or decrease? It's a decrease. We agree? So this is a decrease in what we have. There's a relationship between our growth factor and our percent change. And we're going to talk about that here in a minute. So our growth factor equals 100% plus or minus our percent change. Okay, the reason why we write plus or minus is because we could be adding or we could be subtracting. Okay, so our growth factor is going to equal 100% plus or minus our percent change. All right, let's do some math. So based on what you read here, what is our A for this problem? What is our initial value? Our initial value is what? 10 pounds. Do we see that? So 10 pounds is our initial value. What is our growth factor? What is our growth factor? 100% what? And what is our percent change? And we set it to what? It's negative. Why is it negative? It's a decrease. So our growth factor is going to be 100% minus 20%, which leaves us as what? 80%. And how do I write that as a decimal? 0.8. Are y'all with me? Have I lost anybody? Okay, so if we were to make a table, and we would have our table, we would have this as our weeks, and this would have our number of apples, right? At 0 week, we have 10 pounds. How would I find out what we have at week 1? Not to the power, I would just multiply by 0.8. So I would have 10 times 0.8. And that would tell me how many apples I have left after week 1. Does that make sense? So after week 1, how many apples do I have left? What's 10 times 0.8? 8. I have 8 pounds of apples left. Does that make sense? So on week 2, on day 2, is she eating apples a day, right? Okay. On day 2, I don't know why I put weeks. days. Day 2, I'm going to take 8 and multiply by 0.8. So how many pounds of apples does she have left on day 2? 6.4 pounds. Okay, and then I would continue this, but do I want to keep using the table? No, we want to create a model so that we can figure out how much she would have after a week. And a week equals how many days? 7 days. So we're going to create our model. And to create the model, you just need to know your A and your B. Do we have our A and our B? Yes. So our Y, which is our amount of apples left, equals our initial, which is our A, 10, times our growth factor, which is 0.8 to the X. And this is what we can put in and calculate. So if I want to know how many after 1 week, which equals 7, which is going to be our X value, all I'm doing is what here? Plugging in. So we have 10 times 0.8 to the 7. So I'm going to go to my calculator. And I put it in, ignore all of that. So I have 10 times 0.8 carry, that's not an 8, that is a 5, bless you, to the 7. And how many apples does she have? About 2.1 pounds after a week. So this is approximately 2.1 pounds of apples left. So we found our model, and we found the number of apples after a week. Okay. Yes, no, maybe so. Feeling it? Yeah. Doable so far? All right, I want you guys to try 2 at your table.
It made sense to me, which is, one of my subs the last period, he was a medium. So it makes sense to me.
All right, here we go. Let's talk about it, guys. So remember I said the goal here is you're working backwards. Jenny already did all the work, right? She wrote her equation. She wrote her PFT. And now it wants to know, what is Jenny's equation telling us? So her initial number of people, remember, our initial is what? Our A value. And what is our A value here? 3. So she initially got 3 sick people, right? Oh, A is 3 people. Okay. Our growth factor, your growth factor is your B value. So your growth factor equals your B value. And what's our B value? 1.25. So that's our growth factor. Okay. And then your percent change. And then why is it positive 25%? Exactly. It's an increase, right? Our percent change, the relationship is our growth factor equals, what do we write here? Remember I squared it, growth factor equals 100% plus or minus your percent change, right? So if I know that my growth factor is 1.25, which is the same thing as 125%, equals 100% plus or minus our percent change, right? What plus 100% is going to make 125%? 25. So our percent change is an increase of 25%. Okay, that's us going backwards. How do we feel about going backwards? So we were given the model and we had to interpret the model. Yes? Good? Confusion points. Which part? That's a lot of repeating. Good. So which part? Like, okay, so remember we wrote right here, our growth factor equals 100% plus or minus your percent change, right? So if I know my growth factor, I can find my percent change by subtracting it from 100. So if my growth factor is 1.25 and 1.25 as a percentage is 125%. So 125% equals 100%. So 100% plus what makes this growth factor? Yeah? Are we good? All right. So the answer would be 25%. Initial people, 3. Growth factor, 1.25. Percent changes, 25% increase. All on good page? All right. Now, next one, we have Rohiza sold her stamp collection and every year thereafter donates 30% of the remainder of this money to charity. If her stamp collection sold for $6,000, how much of the initial amount will she have left after T years? Okay. So if we were to make a table of this, so these are her years, this is how much moolah she has left, right? All right. So at year 0, what was her amount she made? 6,000, right? And we want to know if this pattern was to continue, what would happen, right? So 6,000 is her A. How do I find her B? 100%. Good job, because there we go. That's because 30% is our what? Percent change. And if she's donating, she is losing it, right? So it's 30%. So therefore, our growth factor equals 100% minus 30%, which is 70%. And how do we write that as a decimal? 0.7. So if I wanted to figure out year 1, what she has left, I would multiply by 0.7, right? So 6,000 times 0.7 gives me what's 6,000 times 0.7? 710. 4,200. So after year 1, she's left with 4,200. And if I wanted to find the value of 2, I'll continue, multiply by 0.7. So what's 4,200 times 0.7? 2,940. And continuing, right? So did we see how the growth factor works? How it's our ratio? Yeah. Okay. Cool. Now it wants a model because it says after T years. So it wants us to write this as a model. So what would be our model for this? We would say y equals what? 6,000 times, and that's it, right? So we know that every year. So at year, if they ask for year 3, year 4, year 5, could I easily calculate that? Yeah. Yes, without having to continue the table. Does that make sense? All right. Okay, I want you to do 4, but 4 is a little tricky. Okay, it's only a little additive. Here we go. Suppose that one of Peter's social media posts receives 45 likes on the first day of a particular month, and that the total number of likes increases by about 50% every day. Write an exponential function model for this scenario and use it to estimate the number of likes Peter would have on the 25th day of the month. Okay, this is the only little change in our model. Notice here that it's 45 likes on the first day, because is there such thing as a 0th day? No. So there isn't a 0 in this problem. There's a 1. Does that make sense? So our difference here in our model would have to be y equals a times b to the x minus 1. And that's because we do not start at 0. Does that make sense? Yeah. Okay, everything else is going to be the same. So you're going to find my growth rate, my initial, my percent change, and my growth rate. Ready, set, go. calling you back together, beautiful people. All right. So we know our initial is what? 45 likes. Good job. Okay. What was our percent change? 15%. So because that's our percent change, what is our growth factor? 1.15, because it would be 100% plus 15%, which is 1.15. Yes? So what's our model? And it's x minus 1. Why are we x minus 1? It's not at 0. Our initial is not at 0. Are we okay with that? Okay, so there's our model. Did you find out how many likes we would have on the 25th day? 1,200 what? So 288, because can you have 88? But do we need the 0.1? Can you have 0.1 of a like? No. So just be on the 25th day, he would have approximately 1,288 likes. Yes? Feeling it? Did we all get that? Okay. If you did not get that, let's look at how you should have put in the calculator. So you should have put in 45 times 1.15. Carry. Now remember, my school's a little janky. My calculator's a little janky. So I have to put parentheses. And I'm going to put 25 minus 1, or I could have just put 24 because I know what that is. And then I hit enter and I get 1,288. Yeah? If you didn't get it, do you see your error? No? No? Yes? Closed mouth don't get fed. So you can stare at me, but if you don't say anything. All right. We're going to do our last one. All right, here we go. We have Dante's favorite video game store is running a clearance sale. Every week until everything is sold, the store owner is going to reduce the price of the remaining merchandise by 25%. Dante figures that he should wait 4 weeks to go to the store because then the merchandise will be 100% off. All right, construct a mathematical argument involving an exponential function to explain whether Dante's correct or incorrect. Okay, what do you think? Is Dante... He's I'm glad y'all knew that. All right, so we're gonna first prove that he's wrong with the table, and then we're gonna write the model. Okay. So first thing we're gonna do is talk about the initial here. The initial here, we don't have a price that we're working with. Does that make sense? So the initial here is just 1. And the reason why it's just 1 is because this rule is gonna apply to anything in the store, the 100%. Does that make sense? It's a sale that applies to everything in the store. So our initial is going to be 1. What is our percent change? 25%. So our percent change is, it's going to be a decrease of 25%. So therefore, what is our growth factor? What is our B? 0.75. Good job. Okay. So we know that. So let's prove them wrong with the table. So table-wise, it looks like this. Your table you're setting up is going to be in weeks, and then the percent that you're paying. So it's the percent that you pay. On week 0, everyone is paying 100%, right? Because nothing's on sale yet. Does that make sense? On week 1, that's when the sale begins. So in order to find the cost of week 1, that is 1 times 0.75. Why 0.75? Because it's our what? It's our growth factor. Okay, it's the weeks and our percent pay. Okay, so on week 1, everything is 75%. You're gonna only pay 75%, right? That's still, it's a little bit of a sale, but is it a big sale? No. On week 2, how much is everyone paying now? Because you have to put 0.75 times our growth factor, which is 0.75. So what's 0.75 times 0.75? Is it all right if I just 0.56? Okay. On week 3, so now you're only paying 56%. On week 3, what are you doing? 42.56 times 0.75 equals 42. Still not free. He was very wrong. It's 42. All right, week 4. What is Dante going to walk into the store and have to pay? 31%. Womp, womp, womp. He thought he was going to be getting it for free, but how much does he have to pay? 32% of whatever the price is, okay? Now, we're going to use our model to figure out how many weeks would he have to wait for everything in the store to be free.
What does it say?
Which part?
The bottom.
32. Okay, so our model is y equals 1 times 0.75 x. Okay, let's go and see how long Dante would have to work. What's the likelihood of this company having a cell that long? Slim, but let me clear my calculator. Second plus 7, 1, 2. So I'm going to go to y equals, and I'm going to put in 1 times 0.75 to the x.
Miss, when I did that, you went out there earlier, I tried to plot and I did something there. It didn't work.
I don't know what you did. All right, we're going to look at the table and see how long it takes for us to get 0. Before I look at my table, I'm going to change it to mode, and I'm going to round it to 2 decimal places because that's percentage for stores, right? No store is going to be like, oh, it is 33.3% off today, okay? So I'm going to change my mode to 2 decimal places. So from float to 2. Now I'm going to go look at my table. All right, were we right so far? Yep. And how many weeks is it going to take until it's 0? 19 weeks. So when he walks in 19, almost 5 months later, the store's out of business. Let's just be honest at that point. They're probably sold out. But we would tell our friend Dante, sorry, sir, you would have to wait how many? 19 weeks until everything is 100% off. And I'm pretty sure by then the store would be closed. I know. All right, how do we feel? Okay, so if you have a quiz on this on Tuesday, how do you feel about that?
These studies talk about again.
Yeah, we'll keep practicing with B. Part B is a more practice, but yeah. Okay.